Okay, let's work on the closed feed water heater. So a closed feed water heater exchanges heat transfer, but the two flows remain separate. So I've got one flow, a fraction coming off the main flow here, and the fraction is related to this total mass flow in the power plant. So this represents the total flow coming out of the steam generator, and so this is a given value, so I'm going to refer to that in my fraction. So I'm taking 10% of that total flow. So let's start with an easy one. This property of this in this line doesn't change because all I'm doing is taking off a fraction of the flow. So that's just going to equal this. So it's still state 2, and that means that all my properties are staying the same. So first let's calculate those properties. So equals water, what I'm given is pressure and enthalpy, and I want temperature, and the pressure is here, enthalpy is here, and then I can copy that if I want, or just retype it, and I'll paste it. I have to hit escape first. Paste it here, and change this to entropy. So this is still referring to these two cells. Then a different way to paste is, well, let's just do this. Equals this, and just drag this corner. So this is pasting that formula and all these, but the formula is actually changing. So it's referring to, instead of this referring, all of these referring to that cell, when you copy it, it will scroll down. So this refers actually to that cell, which needs an equation. And the quality is a function of the pressure and the enthalpy. Now, to double check, you should occasionally go calculate some of these values from the superheat tables and from the saturation tables. These are all superheated values. So now these are just all copied over here because the state didn't change. Now down here the state does change because I'm heating this stream. So this equals whatever state that is plus 1. So this is a new state. It'll have different values than here. Now the pressure in this line doesn't change, so that one's easy to calculate. It's got the same pressure as this state. The enthalpy we're going to have to calculate. So let's move on to a closed feed water heater. So in a closed feed water heater, we have two separate streams. So we've got one stream coming in here, coming out as a saturated liquid, and we have a valve here which has a pressure drop. And then we have a pipe that goes all the way through. And so we've got, we'll use the states that are labeled here, 2, 9, 10. These two aren't labeled, but I'm going to call them 11 and 12. All right, so let's draw a system boundary here. I'm going to leave the valve out of it for right now. And so I have the mass continuity equation. If it's steady state, summation m dot I minus summation m dot E equals 0. And so 0 equals m dot 2 plus m dot 9. Those are both inlets. And then I have two exits. Minus, and I'll just put parentheses around these. So minus the two exits, which is m dot 10 and m dot 11. Okay, now the first law. So I'm assuming steady state Change in kinetic is 0. Change in potential is 0. Across this boundary, there's no heat transfer. There is heat transfer inside, but heat transfer 0, there's no work. Right, so given all those conditions, we have that 0 dECV dt equals Q minus W, those are both 0, then plus summation m dot I hi, I don't have more terms because these are 0, minus summation m dot E he. Right, so now I can use those to find an unknown state. So the unknown state I'm after is this H10. So this gives me 0 equals m dot 2 H2 plus m dot 9 H9 minus m dot 10 H10 minus m dot 11 H11. Actually, let's make that plus. Put it in parentheses. All right, now something else I can just note from using this equation again. If my system boundary was just this pipe, I can see that m dot 9 is equal to m dot 10. And whatever flows into this side has to come out this side because they're not mixed. So m dot 2 equals m dot 11, and m dot 9 equals m dot 10. So otherwise it looks like we have too many unknowns. All right, so now we can start putting some things together in the spreadsheet. So first thing would be, let's solve for this enthalpy here. So we've got the flow here is m dot 2, and we have the enthalpy here. So m dot 2 and H2 are known. M dot 9 is given here, and H9 are known. So m dot 9 and H9 are known. Then we have m dot 11, which is equal to m dot 2, so that's known, and m dot 10, which is equal to H9, so that's known. So we have two unknowns now. Now H11, I don't have a place for that on this spreadsheet. So the enthalpy here is kind of built into the system. So let's calculate that, but we'll put it in this equation rather than on the spreadsheet here. So we need to find H11. And what this trap does is it adjusts the flow so that this state that's coming in, it always comes out as a saturated liquid. So it's going to come out here as a saturated liquid. So at what pressure? Well, at this pressure. So H11 equals HF at P2. So saturated liquid at this pressure. All right, so now we have everything we need. We solve for H10. So H10, if we bring that term to this side of the equation, it'll be positive. And so we'll write M2 H2 plus M9 H9 minus M11 H11, and then I brought this to the other side of the equation, so it really had M10 H10, so the M10 I'm going to divide both sides of the equation. So that should give me my H10, so let's try that. Equals M2, and we probably want to start a parenthesis here for my big numerator. M2 times H2, the times in there, M2H2 plus M9H9 minus M11. Now M11 is what's coming out, which is equal to what's coming in here. And actually I said M2 is what's coming in, but that's not quite right. So M2, this is what's coming through this pipe. I need to know the fraction here. So both of these terms, I'll leave that one for a minute. This one would be this fraction times the one it's a fraction of. So we're saying take 10% of this, so that's that mass, and then that, click here, is going to be the same value, so it's equal to that times that, so that same fraction of flow times the enthalpy, which is the enthalpy saturated liquid. So we're going to use water, specify the pressure, we want HF, so the saturated liquid enthalpy, and we have to specify where the pressure is. It's the pressure of this flow up here, and that's my entire numerator divided by m dot 10, which is this flow here. This is that return line that's coming. And that should give us the enthalpy. Now, something a little wrong there, so let me double check what I've got here. So I've got 10% of this flow. Let's just double click this. So 10% of that times the enthalpy. So I've got the wrong term here. I replaced the wrong one. I did m dot, so left the m dot. So times this enthalpy. So this is 10% of this, G2 times B27, times this enthalpy, which is this term here. So M2 is multiplying these two terms together. Then times H2, so that's the first term. And then the second one is M9, which is this one, H19 times the enthalpy is kind of hiding under here, minus that same mass flow rate, so M2 and M11 are the same thing, times HF, and that should hopefully be better. There we go. And now I can get these values from these two. So equals water, pressure and enthalpy, temperature, specify the pressure and the enthalpy. And I can just copy that if I want. I'm going to hit escape and then paste. And that gives me the temperature. What I want is the enthalpy, or entropy rather. And then the quality, X at this pressure and this enthalpy. And it doesn't like that extra character there. So negative 532, which means it's a subcooled liquid. So what I'm heating here, it comes in as a subcooled liquid and it leaves as a subcooled liquid. But it has a little closer to saturation. You see it was very subcooled, now it's less subcooled. So we do the same thing over here, calculate those equations again. So pressure and enthalpy, and I want temperature. Just double check that that's the right cell, so that didn't work. So what I can just move these over here. Probably safer just to retype them. So pressure, enthalpy, temperature, and this is the pressure, this is the enthalpy. And then equals water, pressure and enthalpy. I want entropy, specify the pressure and the enthalpy. And the quality, I can just copy this formula. Copy, and it should, if I paste the first one, it'll reference these values, which is what I should have done there. And then these, this flow here equals whatever was here, so that, there's something happens to be there, plus whatever's coming out of here. And what's coming out of here is what came through here, so that's this times this. And that should work, except now I realized I made a mistake here. So you might have been wondering, how could this be the same? So this one also equals this minus this times this. So I took this flow and I subtracted 10% of this. Now you might say, well, that equals that, but it doesn't have to be. This could be 90. And it still takes 10% of this, so it's still going to take 10%, not 9. Otherwise, if you reference to this, it'd be 91. So I'm going to leave this the way it is. And now there's one other way I could have calculated these mass flow rates. Instead of referring to this every time, is just refer to it that one time here, and then these, where I use those cells, the other way to do it would have been to take this cell and replace it with those two as this minus this. So that would also work. And then, don't know if I used it twice. I think I did, so I probably, if I'm going to replace it, I probably should replace it both times. And you don't have to change this, but I'm going to go ahead and do it. Okay, so just typed equals instead of a minus. Okay, so that didn't change anything there. And then this one, I could also change it here. So and there's one slight advantage of doing this, so I'm going to go ahead and change them. If you want to, you can change them, you can leave them. Probably in thermo too, you're going to change them to the other when you build the whole power plant together, so might be worth doing it that way. So once I've defined this cell, now I just stay referencing these rather than coming back to that one. All right, and then finally, so this is all the flow here is coming in here, it's changing state. So it's not changing the mass flow rate because this is a fixed pipe that doesn't allow flow into it. So this just equals whatever this is. And then finally, this mass flow rate times the enthalpy. So this equals this times whatever the enthalpy is here. And actually, since I already added the mass flow rate in, I need to calculate the mass separately if there's some here. So I'm going to say it equals this, which has already been multiplied, the mass and the enthalpy, plus just the mass flow in this pipe, which is going to be that same quantity. So this one minus this one times the enthalpy of what's in here. It's really what's in here, but the enthalpy doesn't change across the trap, so it's going to equal water. given pressure and I want HF. Now, it's no longer saturated here, but I'll calculate the enthalpy here, and it still has the same enthalpy here. And then I specify the pressure, which is this one up here. And those, so now I have, in case there was a, let's say I had 10 kilograms per second here, then this would be 20. And this is still, though, just the 10 that's coming off of this. And so I get 9089.5. So everything matches. There's no work or heat transfer to calculate, so I've got my open feed water heater functioning. Just a quick analysis of this. So my first law, steady state, no change in kinetic, no change in potential, no heat transfer, one inlet and one exit, so that I get that H inlet equals H exit. So that's why I didn't really recalculate this. I just calculated this and put it in for that enthalpy. And then I had another flow coming in here. And so this flow, so really state 12 is what's here. And so this m dot h is really a new state down here that's this stream coming together with this stream, and they're actually mixing. So there may be some change in state there, but all I really need to keep track of is the total m dot coming here and the total h. So that's what I'm keeping track of here. And that will either go back to an open feed water heater or to my condenser. In my example here, it'll either come back in here, or if there's some another open, if this was a closed feed water heater, it would continue on and come in back into the condenser. Right, the other components I think are pretty straightforward, so I'm going to leave those with you. So the condenser, the steam generator, and I guess I'll do one of those. Let me do the reheat, because those are a little different. Those are heat exchangers that actually have heat transfer in them, but they're very simple.